Thank you very much to the organizers for inviting me to this workshop. So I'll talk to you today about SVP and the discrete Gaussian. And this is joint work with Devesh Agarwal, Oded Regev, and Noah Stevens-Davidowitz. And Noah did most of the slides for this talk, though I made potentially the mistake of trying to convert a keynote file to PowerPoint, so we'll see how that works. Right. So let's start with lattices that have been talked about a lot today. So these are just all linear combinations of some basis in Rn. And here you see the two-dimensional integer lattice and basis B1, B2 for it. And we'll just use the notation LB for the lattice generated by B. And the problem that we'll be interested in this talk is the shortest vector problem. So this has also been talked about by Tice and others, so just one more time. So you have the lattice given to you by its basis, and your goal is to compute the shortest non-zero vector in this lattice, and this will be the length lambda 1. So let me tell you a little bit about the kind of status of the provable algorithms for the kind of gamma SVP. So this is approximation factor. So I'll talk to you, we'll just have a table with some hardness as well as algorithms. So of course, it's very important to have heuristic algorithms, but that's just not the focus of this talk. I'll just be talking about provable algorithms. So when the approximation factor goes to nearly exponential, or slightly better than exponential, then this is actually in polynomial time. You can find approximation to the shortest vector of this length. When you go way, way back, so it's known to be hard, not NP hard, but hard in some reasonable notion of hardness to approximate. So this is the decisional version. The shortest vector within this nearly polynomial factor. Already it's in NP intersect co-NP at about root n, and this is Aharonov and Regev who showed that. And crypto sort of begins at approximation factor n. So all of the LWE hardness and SIS hardness and whatever not is generally based on something of the order of an n-factor approximation to the shortest vector problem, or shortest independent set, is hard to compute in the worst case. So this is where sort of you can try and break crypto by finding faster algorithms within this range. Right. And here there are actually provable algorithms that make a little bit of use of the fact that the approximation factor is somewhat large to reduce the exponent below what I'll show you today. And then there is some formula, so Noah wrote this down, I can't really remember if this is 100% accurate, that sort of tells you how things get better as the approximation factor gets bigger. In terms of provable constant factor approximations, again, sort of this same list of authors were able to show sort of provably for some large constant factor approximation, you can get something like 2 to the 0.8 n time. And what we'll talk about today is exact, and here we're going to find the exact shortest vector in 2 to the n time. And we also have another result which says that you can approximate the value, so the length of the shortest vector in 2 to the n time, 2 to the n over 2 time, which is substantially faster, but then we have there is no way that we can see of actually finding such a vector. So we can just tell you what the length is. Okay, so these are sort of the algorithms, the types of algorithms that have been tried. So you have enumeration, sieving, a Voronoi cell strategy that also solves the closest vector problem. And this work which is going to be based on finding ways of sampling the discrete Gaussian distribution at very small parameters. I guess, so it's sort of related to sieving. I mean, in some sense, what I'll show you was kind of an accident related to being frustrated with the proofs, the correctness proofs of sieving and trying to get rid of some of the ugliness. We came to this algorithm here. So in particular, when you're talking about sieving, as Thijs showed you, you have these large lists of vectors that get shorter and shorter, but you have no idea, I mean, at least in a provable sense, what the distribution of these vectors is after 5 steps. And this, makes it impossible or very, very difficult to prove anything rigorous on them. So here we will exactly control the distribution at every step, and that's what will make a difference. Okay, so what is our algorithm for SVP? So let's start with some very nice pictures that Noah drew. So we're going to talk about the Gaussian distribution and the Gaussian distribution with a parameter S. And here we'll start with some large, so this is in continuous space. This is the continuous Gaussian. So we'll start with some large parameter, which the parameter basically determines the width of the Gaussian. And certainly, as you can see, when you decrease the parameter, you decrease the width, it becomes more peaked. And so, the vectors that you would get when you sample from this distribution are shorter. So what is the discrete Gaussian distribution? It's the exact same thing, except that you restrict to live on the lattice. So you just kind of take the continuous distribution and you restrict to being on the lattice. So what does that look like? So here, let's say we have the two-dimensional integer lattice, and we have a large parameter S. And here you can it looks like a continuous Gaussian, right? I mean, if you kind of zoom out and stare at it from far away, you can't really make out that this is so terribly discrete. But then, as you start decreasing the parameter, I mean, you start seeing more artifacts of, the lattice. I mean, the lattice structure starts to appear. And your discrete Gaussian is concentrated on shorter vectors. You can keep sort of continuing this process. And now you're sort of getting to a point where at the very end, maybe this one or that one? Yeah, okay, well, whatever. So you start getting to a point where essentially, the distribution becomes kind of degenerate, i.e. it's going to be fully concentrated on just 0. So if you make the parameter very, very, very small, then the distribution doesn't have enough energy to jump to any non-zero vector, because 0 is always going to be the point of sort of maximum energy. So at that level, your distribution sort of tells you nothing about the lattice. At very high level, also in some sense, it doesn't tell you that much about the lattice because it's kind of like a continuous Gaussian. So we're looking for short vectors where things are still meaningful, and this is going to require a somewhat careful trade-off between the parameter and the kind of geometry of the lattice. And here you can see that, okay, so you do have a lot of mass at this parameter 2 here on 0, which is useless because you want the shortest non-zero vector, but it's basically kind of almost uniformly distributed on shortest vectors. So if you don't land on 0, then you will land on essentially shortest vectors. And that's essentially what our algorithm is going to try and get at. So it's going to try and sample this distribution at the right parameter so that you have like a non-trivial chance of landing exactly on the shortest vector. Okay, so please stop me if you have any questions so far.
May I ask a question? So why is the discrete Gaussian the best distribution? Is that clear? Or? So it looks that, actually it's not, because you have the 0 issue. So
Yeah.
It'd be better to have a bimodal distribution where the peaks are around the shortest vector, right?
Yeah, no, that's a good point. I mean, yeah.
If I give you the length of the shortest vector, can you design a better distribution?
Oh, I mean, well, okay, so basically you will almost get to the point where if you condition on not landing on 0, then it's like almost uniformly distributed on the shortest vectors. So this is certainly an artifact that's non-trivial, and it's true. What will happen is, at the right parameter, you'll have so the optimal parameter, let's say, you'll have sort of probability of half of landing on 0, and then you'll have some exponentially small, but not too exponentially small probability of landing on exactly a shortest vector. But the shell of, let's say, approximate shortest vectors, you will land in with very high probability. So it's really, hitting the exact one is tough, but hitting approximate ones is, the right parameter should be okay. All right. Well, okay, actually, it's not totally true what I said, but that's fine. It turns out that if you balance things correctly, so that means you don't want the distribution to land entirely on 0, and you want the shell essentially containing all the shortest vectors to be basically dominant compared to everything else. You should pick the parameter to be roughly the length of the shortest vector divided by root n. And for those of you who have some intuition about what happens with the Gaussian, the expected norm of a Gaussian with this parameter will be lambda 1, because it's in n dimensions. So you have n coordinates that contribute sort of lambda 1 squared over n mass. So this sort of matches with, where you would want the continuous Gaussian to be. And at that parameter, indeed, if you pick things carefully, you can prove that, the probability of hitting exact closest vector is at least, 1.38 to the minus n. And that comes from, bounds also on the Kissing number, or, more generally, these sphere packing bounds due to Katyabansky and Lemonstein. Okay. So now it turns out that the discrete Gaussian, when you look at it for sort of very large parameters, so not bigger than, say, the length of the shortest vector, but bigger than the length of the nth successive minima. So basically, when you already see a full basis of the lattice and then some. We do understand the discrete Gaussian quite well in that it really does look like a continuous Gaussian. And at these parameters, if you have a good basis, which in cryptographic settings, you're often given something like a trapdoor basis because you built the lattice yourself, we do know how to solve or sample from this distribution in polynomial time. But actually, even if you allowed exponential time, it's not like we knew how to do much better than this. So these algorithms use a basis and use some form of randomized Babai rounding on the basis and show that that's a good approximation to what the discrete Gaussian distribution would give, but there is no algorithm to go below that. Okay. So our goal will be to start from a really bad basis of the lattice, say given by LLL, which will allow us to sample essentially at some s that's, say, 2 to the n times lambda 1 of L, roughly speaking. And we're going to try and turn these sample, so this is sort of where things are easy, and this is where things are hard. And the goal will be to turn samples that we get in the easy regime into samples that will solve the problem. So we'll be doing something that is kind of like sieving, but to Gaussian samples to try and make samples shorter. Okay. And in this language, it will mean that we're trying to make the parameter of the Gaussian that we're sampling small. Okay. So how could you do this? So if you had the continuous Gaussian, if you sampled from a Gaussian and just, divide it by 2, you will indeed get a Gaussian where the parameter is divided by 2. So that's sort of, an easy way to turn a continuous Gaussian into a smaller continuous Gaussian. Now, of course, you run into problems when you try and do this on the lattice. Why? Basically because you will sample a lattice point from the discrete Gaussian, and then you try and divide it by 2, and you will notice that you're not in the lattice anymore. So clearly, that won't work, without a little extra thought. Okay, so what if you just, for sanity, condition on the result of dividing by 2, you condition it on being in the lattice. So this means that the vector y that you sample is actually inside 2 times the lattice. So if you do this, you will in fact make substantial progress. So basically, this is a trivial computation. The new, this should be, so this is an x, okay. So the new parameter will essentially be divided by 2, which comes out here as a minus 4, which makes the distribution even more concentrated. So if you did this, certainly you would get a discrete Gaussian with a smaller parameter. The unfortunate thing is that you have to wait until you land inside exactly 2 times the lattice. And this will, when you start, will essentially take 2 to the n vectors before you even see 1 that lands in 2 times the lattice, so it'll take forever to even do this 1 time. But if you think about it...
So now n is the number of iterations that you do, right? It's not the...
No, this is the... So here we're in n dimensions, and 2 to the n here is how many times you need to sample, let's say, above smoothing before you see a vector in 2 times L. And this is just basically because all the cosets are equally distributed, and there are 2 to the n of them, so that's how long it's going to take. So n is the dimension of the lattice, yeah. But okay, so let's say if you were thinking about, waiting 2 to the n times, so you've sampled 2 to the n vectors, you have a lot of them. It's kind of stupid to throw them all out except for the one that lands in 2 times the lattice. You have some of them that you can hopefully combine together to make things shorter, okay? So, in the Gaussian world, you will be able to do something like this. So in the continuous Gaussian world, so you'll find 2 samples, you combine them together and divide by 2. Okay, so this is just averaging. So here, it's also very simple to show that when you do this, the parameter decreases not by 2, but by root 2. So the goal will be, to find samples like this that you get from the discrete Gaussian, where you'll be able to do the same thing. And this will make sense somehow because we'll be sampling something like 2 to the n vectors. So you can sort of expect to see some that you can average where the average will remain inside the lattice. Okay? So what happens when we average 2 discrete Gaussian distributions? So again, for trivial reasons, you're not always going to be able to average. So that's pretty clear. But what happens when you can? So let's just condition that we have 2 discrete Gaussians such that when we average them, they land inside the lattice. So what is the distribution that we get when we average those 2 things? So when is it that we have, to be clear, averaging 2 lattice vectors being in the lattice? So this is very, very easy. You just basically notice that if you write both vectors out in essentially any basis, and you look at their coefficient vectors, then when you average them, okay, obviously they're coefficient vectors average, and you need all of these to be integers, right? So the only way that this can happen is if all of the coefficients have the same parity, modulo 2, which, more abstractly means that the two lattice points are off by a vector that is inside 2 times the lattice. So this is very simple. So average 2 lattice vectors that's in the lattice if and only if they're the same mod 2 times the lattice. So what if we condition on sampling sort of a pair of lattice vectors? So here we're gonna, here I'm sort of imagining that, we have a lattice being Zn, and being Z, and we are sampling 2 lattice vectors, so 2 points in Z, y1 and y2, so that's just, if you look at the full space of that, that's a 2-dimensional grid. I mean, you can do this obviously in more generality. And I'm going to look at the subset of this such that when I average the sort of 2 coordinates corresponding to this pair of lattice points, that be in the lattice again. So in this picture, what that corresponds to is the pairs of points where, or the points where the 2 coordinates have the same parity. So this should be the odd coordinates, so where both coordinates are odd, and this is even. And if you kind of remove everything else, it turns out that you get another lattice. So if you kind of look at the cross product of 2 lattices and you restrict to the pairs of lattice vectors that have the same parity, it is again another lattice. So this is the lattice that we'll call L dagger. Okay, so you can see it's a lattice just because when you add 2 points inside here, they're still inside here. So this is the set that we're going to condition on. So that means we're going to look at the kind of joint distribution of the discrete Gaussian when, or of sampling 2 discrete Gaussians conditioned on landing inside the lattice when I average them. So these are the sort of pairs of points that you can get. And now let's look at the kind of generalized averaging map. And this is basically trying to mimic the proof that the average of 2 Gaussian vectors is again Gaussian. So this averaging map is here sort of the term that we're going to use. Here's the term that we're going to end up throwing away. But when you put them together, the nice thing is that this map is kind of like a rotation by 45 degrees. Okay, so if you apply this map, that sort of rotates this kind of, restriction of the cross product and shrinks it a little bit by root 2. And if you notice this picture, okay, if you were to add more things again, is exactly the lattice, Z cross Z again. And this is very easy to prove algebraically, that when you apply this transformation, you essentially get the lattice cross the lattice back. Okay, so you started with the lattice cross the lattice. You conditioned on being on the pairs of lattice vectors where when you average them, you're in the lattice again. Then you looked at this averaging map, and you get the lattice cross the lattice again. Okay. So let's think about what that means from the perspective of distributions. So first, we're conditioning our pairs of lattice vectors to live inside here. And then we apply the averaging map, we get the lattice cross the lattice again. So if we look at what happens to norms, so if I have 2 pairs of lattice vectors and I apply this kind of averaging map, the norm essentially stays the same, except that it drops by root 2. Because this isn't quite a rotation, there's also a shrinking. And this is also very easy to check. So that means that if you sample 2 lattice vectors from the discrete Gaussian restricted to this dagger lattice, which is what it means to restrict to the event that when I average them, I stay inside the lattice. Then when I apply the averaging map to that distribution, I'm going to get, again, a discrete Gaussian on the cross product lattice, because that's what this is going to go to. But instead of having, because the norms drop by √2, to get the sort of original probability back, it means that the parameter dropped by √2. This is just to say that, I have to, this will be a discrete Gaussian, when I work things backwards, but the norm of this is √2 smaller than that, so when I work things backwards, that means the parameter in this lattice will be scaled down by √2. So that's great. So that's progress. So this is, the formula for what, the discrete Gaussian with this parameter should look like. So if you work things out, that's what you'll get. So averaging two lattice vectors that sort of can be averaged is helpful. Okay. So let's think of this proof as kind of a procedure to stitch together pieces of Gaussians to make a new discrete Gaussian. So what's going to happen in the next few slides is that we're going to find a way of sampling, we're going to be sampling a lot of discrete Gaussians, so something like 2 to the n of them. So we'll start at some very large parameter. And then we'll find ways of combining pairs of these so that we get a lot of independent discrete Gaussians with a smaller parameter again in the next step. Okay. So let's just think a little bit about what stitching together, how you should think of combining the different pieces for it to make sense for the next step. So this is the probability so this is what we just showed, this probability. So this is, I have two independent discrete Gaussian samples, I average them and I'm conditioning so that the average is in the lattice. That's sort of what we analyzed in the last few slides. So this is exactly the probability that the discrete Gaussian with parameter divided by √2 equals y when y is in the lattice. So this is that probability. So now let's just expand this out. So what this is, or at least proportional to, is if I want to get y, I basically have to sample y1 and y2 from the same coset mod 2 times the lattice. So that means they have to have the same parity. So they both, y1 and y2, both have to land inside the same coset, so you get this square. And then conditioned on that, and this conditioning is described by saying that y1 and y2 are inside 2 times the lattice plus this coset, plus this parity, then that should equal y. Okay? So if I'm thinking about stitching together pieces of discrete Gaussians to make one new discrete Gaussian, so if I want to generate one sample, you can think of the following kind of abstract process, which we will use, which is basically I want to generate one sample from this at a smaller parameter, which is this is the same probability. So what I should do somehow is, if I'm going to stitch together pieces to make a new distribution, I'm going to sample a coset, so one of these parities, with probability proportional to the square that parity appears. So that comes here. And then once I have the parity, I'm going to average 2 discrete Gaussians that live in that coset. Okay, so that's what you would need to do to generate a single discrete Gaussian sample at a lower parameter. All right, so now what happens when we're trying to think of this framework and use it when I have a lot of discrete Gaussian samples? So here I have like y1 through yn discrete Gaussian samples, which is like 2 to the n. Okay, so this is, you should think of this as being very, very large. So in particular, this should at least at the beginning fill up all the parities. So every parity should basically be represented at the beginning. So we're going to first sort of bucket the samples according to their coset mod 2L, according to their parity. And then we'll repeat the following abstract process many times. So we'll sample a coset, so this is a specific parity, with probability proportional to the squared probability of landing inside this coset. And then we will pick some yi and yj that happen to live inside that coset, average them, and output. Okay? And then we will remove these yi and yj from the list. Okay, that's kind of very abstractly what you would like to do. Now there are a few or many problems with this. Firstly, you don't actually have direct access to this squared distribution. So if I want to have access to this distribution without the square, I take one of my samples and I just see which coset it lands in. Okay, that'll give me access to the coset distribution just directly without any squaring. Does that make sense? Okay, so I don't actually have any direct access to this squared distribution. And second, you might be worried that, at some point I'll run out of samples in each of the cosets. So I might not be able to do the second step even if I did have access to that squared distribution. So I'd sort of run out of vectors. And there are all sorts of issues with dependencies in between the samples and this kinds of stuff that also could happen. All right. So these are the two issues. So now I'm going to try and describe to you a rejection sampling approach to solve this problem. So to solve both problems. So first I'm going to describe a really stupid rejection sampling approach that doesn't really achieve anything that's non-trivial, but at least shows you what the rejection sampling thinking is, which is that, sort of first pass, you're going to sample from this distribution of cosets, so the original distribution, so without the square. And then the rejection sampling framework is just think of, now that I've sampled this coset, so, I'll show you the implementation in a second, I'm going to accept this coset with probability equal to the probability of landing inside that coset. So this will add the square. And if this coin, goes to 0, I reject, and if this coin with that probability goes to 1, I accept. So the implementation of this is, I have one sample from the discrete Gaussian, I look at what coset it's in, I sample a second discrete Gaussian, and I output C if y1 is congruent to y2. This will implement that scheme. But the thing is, this doesn't implement anything non-trivial. This is almost the same as waiting for a lattice vector to be divisible by 2 to begin with. So how can we make this slightly more non-trivial? So the point is all I need is that all these kind of rejection probabilities should be proportional to what they need to be, but they don't need to be exactly this. So I could move this rejection probability up by any constant as long as this remains a probability, meaning it remains less than 1. And I would be somehow, increasing the probability that I'm not throwing away vectors. So what's the sort of optimal thing you could do in this framework? So instead of accepting C with probability proportional to the weight of its coset, I'm going to accept it with this probability, but divided by P max, where P max is just the maximum probability of landing in any coset. So this will ensure that this number is always less than 1, and it pushes it up as much as humanly possible so that, I'm decreasing the chance that I'm throwing away vectors all the time. So in particular, if I land in a coset that is the heaviest, then I will accept with probability 1. Okay, so at the beginning, the heaviest coset will not have higher weight than anybody else because we're basically completely smooth in this coset distribution. So every coset will have weight like 1 over 2 to the n. So then, at the beginning, if I didn't do something like this, I would reject with probability, at least 1 minus 1 over 2 to the n. Whereas here, if I can do this P max trick, then I will reject with, probability close to 0. So it makes a big difference to do this. But of course, I mean, how do you implement this, right? I mean, this is not as trivial to implement as the previous scheme. So now I'm going to try and explain to you what this implementation looks like. Right. Okay. So the first thing that we're going to do is we're going to take our samples and we're going to break them up into, sort of chunks that we will use to compute useful statistics, and the chunks that we will use to combine together to make new discrete Gaussians. So the first thing that we'll do is we'll take, say, I mean, these are kind of approximative constants, like the first m/6 vectors to estimate the largest probability. So roughly speaking, if you estimate, if you guess that the largest probability should be a half, and you sample, m/6 discrete Gaussian samples, there should be a coset or a parity that appears, m/6 times 1/2 times. Okay, and if there isn't, then, you've overestimated the maximum probability and you should decrease your guess. So this is quite easy to do. So then we're going to use most of the samples to kind of create a table which is going to count in phases how many samples land inside buckets where the buckets are labeled with the different parities. So if I know the maximum probability, so I know that, if I have m samples, I'll never see more than m times p max samples that land in any one bucket. Okay? So I'll basically sort of, these buckets are basically going to be estimating the probability of landing inside that bucket, but scaled up by some factor 1/p max. So how do I kind of generate, these coins that scale up the probability of landing inside a bucket? So I'm just going to, for each bucket, think of sampling, 1/p max number of samples and seeing how many of them land inside each bucket. If you look at the expected number of samples in each bucket, it's exactly the probability of landing in that bucket times 1/p max. Right? So this does the boosting up. And if we're going to use these as kind of pseudo estimates for our probabilities, I'm going to need to make sure that I have enough of these estimates to use in the next stage. And in the next stage, basically, I'm never going to use any bucket more than m times p max times, because that's how many times I expect the heaviest bucket to appear. So it's okay to sort of make a table with at least this many copies of an estimate for this probability. So this is sort of to keep everything independent in some sense. I'm going to make this table that has, for every bucket, every parity will have like m times p max estimates. And in each kind of slice of this, I'm going to use 1/p max samples to estimate, what the probability of each of these buckets is. So if you look at the total size of this table, it has size m/3 because it's 1/p max y times the number of samples you need is going to be 1/p max times m times p max, which is like m/3. All right. So this is what I'm going to use to kind of build these boosted up estimates for each of the probabilities. Okay, so the first part is I'm going to use, essentially, most of the samples to compute our estimate for the maximum probability. We're also going to compute all these bucket counts. And then for the remaining samples, what I'm going to do is very simple. So I have the last m/6 samples. I want to use what I have from computed before to do some combining. So I take this, one of these last m/6 samples. I look at its coset. I look at the first, unused bucket count for that coset. So Remember, for every bucket, I have a row of that table, and I'm going to go to the first kind of column of that table where I have not used that count before. Right? This is to make sure that everything stays independent. So I look at this bucket count. The expected number of people in this bucket is exactly the probability of landing that bucket divided by Pmax, because that's how many samples I use to generate the count. And so with probability the minimum of 1, so this, so it could be that there are, a lot of samples in this bucket. So the minimum of 1 and the bucket count divided by, say, 1,000. This is really going to be a polynomial, but this is just to make sure that I'm always scaling this number to be less than 1, because otherwise it's not a probability anymore. I'm going to output yi plus some yj divided by 2, where the yj is one of the samples that contributes to this bucket. Okay? So if one of the samples contributes to this bucket, it has the right coset, and that's how I'm going to implement this rejection sampling strategy. So there's this isn't like really a full description. This actually has to be polynomially small. We're actually going to be throwing away sort of most of the samples at every step. And we have to use some tricks to ensure that everything is independent, but that can be done. This is roughly the idea. Okay.
Daniel, may I ask something? So you're kind of estimating how many things land in one bucket, right? As far as I understand. Do you do it because you don't know the distribution, or do you do it? I mean, I would expect that it's evenly distributed, but it's not.
Yeah, so at the very beginning it starts evenly distributed, but then once you get to smaller and smaller parameters, it starts to concentrate on like essentially one bucket.
Okay.
So the origin is always like even in every parity. So the bucket corresponding to sort of 0, 0, 0, 0, 0 is going to be the heaviest at some point. And it's not like we know how this is going to evolve. So it's very, it's delicate. I mean, yeah. So above the kind of smoothing parameter, assuming that things are uniformly distributed is fine, but the moment you go below that, it starts changing in uncontrollable ways. Or, well, at least ways that are not obvious to control. Okay, so how many vectors does this output? Okay, so we're only so we sort of lost a constant fraction to computing certain statistics. Really, that's more like we lost a 1 minus a polynomial fraction, but whatever. But sort of for the remaining samples, we need to know what the probability that we didn't reject is. So, as in the probability that we accepted a sample is, this sort of squared probability summed over all cosets, right? Because that's, you just imagine one step of the process. I sample a coset, I reject it with probability, this not squared divided by Pmax. So when you look at the probability of rejecting any one sample, it's the sum over all the cosets. And you try and understand what this could possibly be. Okay, so you would like this to be large because you'd like to keep, a lot of samples for the next step. Now you can actually compute a worst case bound over any distribution, and it'll tell you that the worst case bound over any distribution for this quantity is actually 1 over the square root of the support of the distribution. So the support of the distribution here, there are 2 to the n cosets, 2 to the n parities. So this is, 1 over 2 to the n over 2. Okay, so that's kind of terrible. So this is very, very bad, right? I mean, so we're saying, okay, in one step, we can essentially lose everything. And actually at this point we kind of lost hope for a while, and we thought this was kind of a stupid idea. And then Oded magically saved us by noticing that these estimates are not completely arbitrary, right? So it actually sort of is true that in any one step you can lose roughly, a 1 over 2 to the n over 2 fraction of your samples. But it turns out that if you look at this process over a huge sequence of steps, then it's also 2 to the n over 2. And this is magical. Like, we have no idea why this happened, but it did. So this is based, so here's it's an analysis that's it ends up being quite simple, and it's just based on the identities that, you get from understanding, how these different probabilities are related to this averaged lattice, so this L dagger. So okay, so let's understand these probabilities a little bit better. So the sum of the squares of these probabilities of landing in the same coset. So here at the bottom you have the sort of total Gaussian mass of the lattice cross itself, and here you have the lattice L dagger, which are the things that you can average, which is exactly this probability. So you have sort of the Gaussian mass of L dagger divided by the squared Gaussian mass. So this is L times L. But if we apply this kind of rotation map, then we know that when we rotate, we actually get L times L, but to recover the original Gaussian mass, we have to scale up the vectors by √2 because their norms dropped. And then you get this formula if you look at it correctly. Fine. So that gives you 2 out of 3 terms. So the third term, it turns out, and this you have to believe some very basic Fourier analysis, that the heaviest coset is always the 2 times the lattice itself. So it's the central shift of the lattice. So if you have a lattice and you want to maximize its discrete Gaussian the discrete Gaussian sum, you should always center it at 0. You should never shift it anywhere. And this is just because the Fourier transform of the Gaussian is positive. It's not a hard thing to prove. So this is the central shift, and that's the heaviest one. So you get this nice kind of ratio of products of Gaussian masses at different parameters for the same lattice. Fine. So now the magic is you can see what happens over multiple stages. And what happens over multiple stages, you get these products, and of course, if anything is going to be true, these products have to be telescoping, and they are. So lo and behold, you have a term corresponding to the first stage, and a term corresponding to the last stage, because we're telescoping. So it turns out that in this, for this last stage, this parameter is smaller than this parameter, so this term is just going to be bigger than that term. And then again, there's some Fourier analytic argument that says that when you scale a parameter by a factor of √2, the Gaussian mass cannot increase by more than a sort of a √2 to the n factor. So this term ends up being bounded by 2 to the minus n over 2. So it says that not only does this kind of loss factor, can it be 2 to the minus n over 2 in any single stage, but over like any combination of stages for infinity, it's also 2 to the minus n over 2. So this is very, very special, and we still have no idea why this is true. And it is the entire reason the algorithm works. And so what this tells you is that somehow if you start the process with 2 to the n vectors, and you ignore all sorts of polynomial losses that we're going to have to incur to, satisfy that things are independent and all those horrible details. If you start with 2 to the n vectors and you run this for infinity, if everything is perfect, you will end up with m times 2 to the minus n over 2 vectors, which gives you 2 to the n over 2 vectors. And magically, that number also happens to be bigger than 1.38 to the n. So you're done.
You have too many.
Yeah. We even have too many. Yes, exactly.
But you also can't start with less, because then you cannot fill the buckets.
Yeah, actually, so it turns out that all you need is to continue the process at any step is to have sort of a nice threshold above the number of samples you need to fill the heaviest bucket. So once you can fill the heaviest bucket and you can estimate the weight of the heaviest bucket, then you can do this analysis.
So the lower bound is the number of buckets, which is 2 to the n.
Correct, right. So at the beginning, that bound is tight. At the beginning, you're at some huge parameter, and all the buckets are basically evenly weighted. And so at the beginning, you need 2 to the n.
You don't need them because you can throw away the low weight buckets somehow, right?
Yeah, I mean, it happens implicitly, exactly. Yeah, at the end, you don't need it. At the beginning, to start this process at all, you need 2 to the n vectors. Okay, so what is the kind of full, schematic of the algorithm? You start with 2 to the n samples at some very high parameter. You use this combiner. You use this combiner to get samples at smaller and smaller parameter until the parameter becomes this magic roughly lambda 1 over root n. And then you wait until and then you basically pick the shortest vector that you've seen in your list at that point. And this, with very high probability, will be guaranteed to contain the shortest non-zero vector of the lattice. Okay, so that's the algorithm. So just to tell you what you saw in this talk, you got a 2 to the n algorithm for SVP. And really what we showed to some extent is that you can sample 2 to the n discrete Gaussian vectors at any parameter in time 2 to the n. I mean, roughly, if you think about what we do. So we start with 2 to the n vectors, and we essentially get to 2 to the n over 2 vectors at any parameter that you could desire. And what additional things do we show in this paper that I didn't discuss here? So it turns out that you can make this combining procedure much more efficient when you're above smoothing. So when everything is equally distributed, you don't actually need to start with 2 to the n vectors if you do the combining slowly. So instead of trying to immediately combine so that you're in 2 times the lattice, you combine so that you're in some intermediate lattice in between L and 2 times the lattice. And this allows us to get an algorithm for the decisional SVP problem. And that's kind of a not so easy reduction. We actually have to sample over the dual lattice and not over the lattice itself and compute statistics of the discrete Gaussian to get this. It also gives us a bounded distance decoding algorithm. So this is trying to find a closest vector to the lattice when you know that the target is a distance less than, say, half times the minimum distance of the lattice, or half times lambda 1. And instead of a half, we can get 0.422, so pretty close to a half. And more recently, we showed that you can extend these techniques with a lot of work to not just solve SVP, but CVP. And Noah also showed that discrete Gaussian sampling reduces to solving the shortest vector problem on random sublattices of your lattice. Okay. So in terms of open questions, what else can you do with this? So you can solve SVP and CVP, so that's pretty cool. I think certainly a very interesting question is, when can you make this faster at all? Also, there is a key question of, whether you, is there any way to tweak the reduction so that you don't need sort of 1.3n to the 1.38 to the n samples to get, let's say, an approximate closest vector? And this would seemingly require you to sort of change the shape of the Gaussian to not be spherical. And another question from a complexity standpoint is, now I feel like the algorithms are getting closer to, some lower bound. But it would be nice to prove some lower bound, that's quantitative. So assuming something like strong ETH or something like this. And I think if you factor the previous MP hardness reductions, you do get something for at least CVP, I think you get some 2 to the Cn, where C is very, very small hardness, and for SVP, I think it might be 2 to the root n, but I think that would be very interesting. Okay, so that's it.